1 second. Okay, Xin, go ahead. You can start.
She's not here.
She's not here? Let me ping her. Okay, I've sent her a message. Does anyone have a even better way to reach out to her? I have her WeChat.
She's coming.
She's coming.
Yeah.
Okay, great. Xin, are you ready?
Yes. So
Okay.
let me share the screen.
You may click the slideshow or whatever. There's a slideshow on the right top. Did you find your slides?
Yeah. Okay.
Okay, go ahead.
So today my presentation topic is about the Bayesian compression for deep learning. So I did some literature review on this topic. So here are the paper list. And for the, as we know, there are many methods in the network compression. So according to the different method, which use the Bayesian method for the pruning, there are a few subtopics. So like for the channel-based pruning with the variational inference. And another one is that pruning as the subnetwork search, and also for distillation. It also use some variational inference for that, and also for the quantization and the dropout for compression. So today I will mainly cover two papers that is use the variational inference for the channel-based pruning.
What's the general idea of this 1, 2, 3, 4, 5 subtopics?
Actually, this is mainly related to the method, to the traditional method used in network compression. I will cover it later.
You will cover each of this.
No, not each. I will talk a bit about how each method, the method in each subtopic. What are those what will those methods do? So. So here is the outline of today's presentation. So firstly, I will recall some basic knowledge about the network compression method, and then I will talk about the problem statement for the channel-based pruning, and then the variational inference. So after that, I will talk about the details in the two papers. Actually, in last semester, I have already talked about why we need to do compression and what is network compression. So I will spend a few minutes to record this content. So firstly, for network compression, it is try to find a smaller network as good as a large one. And the reason why we need to do the network compression are as follows. So firstly, we can, in some spatial device, like the mobile phone, we need to use less resource. And also, we can use the network compression to speed up the inference. Also in last semester, I tried to summarize the network compression in those ways. So what's the target in the network compression? That's it can be the neurons, or it can be the weights. So for the neurons, actually that's the that can be what the output of one layer, and the weight it includes the filter, or it can include the filter or the connection, such as in the fully connected layer. And there is another, is when to do the pruning. It can be before training. That's some research appeared in the recent years, and also it can be during the training. It means that when we train the network, we also consider to make the network become smaller, and the most common way is to do the pruning after training. And for the method to do the compression, there can be many ways. One common way is that to have the importance score, so that the importance score can be on the neurons or can be on the weight. So we can sort the weight or the neurons according to the importance score. And also there can be some other way, like the low rank approximation. And also it's possible to learn how to prune. So for example, that's the reinforcement learning. So this is the overview of the network compression. And for the method itself, and we are going to so the paper we are going to present today is actually can happen at two stages. So the first one is that after training, actually the another paper is during the training. I forgot to add them to this slide. And also for the other method to do the comparison, that can include the quantization and also the knowledge distillation. So for those two methods, there are also some paper use the Bayesian method for that, but I will not cover them today. If we have one additional presentation, I will do it later.
What's the idea of quantization?
So for the quantization is that in general, for example, in the PyTorch, in general, one weight or one tensor is always the float. The type is the float, so it will use 4 byte for each tensor. If we do the quantization, so it's possible to use some maybe one byte, or actually the most common case is just use the binary weight. So it means that for each weight it only use 1 bit instead of 4 byte. So it can make the model set to become much more smaller.
But if it's just 1 bit, that means your weight is either 1 or 0.
Yes, so that will become the binary network.
Okay.
So for the knowledge distillation, that is we there are 2 networks for the it will use the large network as the teacher network and use the smaller network as the student network. It will make the student network to learn the representation of the last layer of the student of the teacher network. So I mean, if I ever give another talk in next Monday, so I hope to cover how to use the Bayesian method in the quantization and the knowledge distillation.
Yeah, we expect you to give another talk on Monday. You don't need to say if.
Okay, okay, I will. So today we are going to focus on the channel pruning. So firstly, let's look at how to define the problem channel pruning. So there is one figure. Actually, that's two that are from 2 convolution layer. In the first convolution layer, we can say that actually there are n channel. So that's from the CI1 to CIN. So I means the S convolution layer, and for the next convolution layer, there are only two channel. So we can say that for the channel based pruning is that for the input that's the S convolution layer, we need to decide which layer we are going to prune. It means that we will not use that the feature map of that layer get the feature map of the next layer. So the general idea to use is that we were going to have a scaling factor for each channel in the S convolution layer. In this figure, we can say that there are blue convolution layer and the orange convolution layer. So for each layer, the scaling factor are different. For the blue ones, in general, they are larger, and for the original ones, they are very close to 0. So and on the right subfigure, that's the convolution network after pruning. Here we need to notice that. So for when we don't have the scaling factor, actually we get the CJ1 and CJ2 from the CIN. With the scaling factor, we need to multiply the scaling factor to the CIN and then get the CJ1 and CJ2. For this network, so the problem is that how to calculate the scaling factor. So there is one way people always do is that they try to optimize, they try to learn the scaling factor during the training. So there is a new loss. In this new loss, it has introduced one penalty for the sparsity. So here we can let's denote the scaling factor as gamma. So there is one extra term, that's the G gamma. For the G gamma, it's equal. Actually, that's the L1 norm. So with the additional L1 norm on gamma, when we train the network itself, it can get on one side, it can get better accuracy with the first term, and also it can get the sparse network with the penalty on gamma on the scaling factor.
The scaling factor is multiplied to the output of each
channel. Yeah.
Okay, so they don't. Okay. So you actually have additional coefficients for the output.
It can be implemented in many ways. So in this paper, actually they use the batch normalization. So we know that in batch normalization. Okay, so here this is the formulation of the batch normalization. So in batch normalization, it needed to it will for the output it will multiply gamma and beta. So this gamma can be regarded as a scaling factor. So for that paper, it used the gamma to as the scaling factor. Actually, the gamma and beta here are also trainable in Pytorch or in TensorFlow. So it reuse gamma as a scaling factor instead of to introduce a new parameter.
But here, if you use batch normalization, how do you? I mean, the scalar factor for each.
Yeah.
For the output of each channel are different. For outputs in different channels are different. Because like batch normalization, they just assume, I mean, whatever a mini batch of.
Yeah. I need to say it more clear. So for gamma and beta, they are vector. They are not a single it's a vector. So assume for
Oh, okay, okay, I got it.
for yeah. So if X has n channel, so gamma is a vector of have the length and beta is the same.
Okay, okay.
Yeah.
So they do the convolution. I mean, the input, for example, the first the input will like is n by d. Do for any example, for example, it's a d-dimensional input. If you do a convolutional layer, it should be a.
So in general, we have a batch. So assume the batch denoted as B and the channel as C. And also because if the input is image, it always a 2D. It always 2D. So in general, the input can be B multiply C multiply H multiply W. So here for each CI and that's it indicate H by W. So in this figure, it didn't show the batch.
Yeah, I'm curious to know because I'm not very familiar with. For example, this is one example, which is an image, right?
Yes.
And then you do, for example, you have C convolutional kernels. I mean, you have C channels. So
Yeah.
after your convolution, it should be something like that. It should be a tensor, right? C
Yes.
times W times H. Then you do the convolution layer again. Wouldn't they first flatten this W by H, or they just do the convolution on this tensor? Because you got a second layer. You have a like another channel like C2 channel.
Yeah.
Like how does the convolution operations work to get another tensor?
So as we know that, so for one filter, I think firstly we need to figure out what's the dimension of the one filter. So let's assume the filter size is 3 by 3. So one filter actually the size is C1 by 3 by 3. So it means that we have for one filter actually we have so this is the input, and for each filter actually there is a small window. Assume that's the 3 by 3.
Yeah.
Slides over the H by W feature map. And for if there are C1 channel, actually the dimension of the filter would be C1 by 3 by 3. So they will slide they will move on the image, and for each such it will produce a 1-by-1 output, and so if the output have the C2 C2 channel, it means that it requires C2 filter to get that.
I'm lost. I mean, from the very beginning, suppose you have sampled a batch B of images. That will be just the B times H times W, right? And now you want to do the convolution with C1 channels. What's the output size?
With C1 channel.
Yeah,
you,
like-
you can determine the output, the number of output channels.
Yeah, I mean, at the beginning, like suppose you have a B mini batch of images, right? So suppose they are of size like W by H. So now I determine the first convolutional layer, the channel will be C1, right? Like C1 times 3 by 3, right? So what's the output size? So I suppose it to be like B times C1 times W times H again.
Yes, no. So, Shandian, actually, it's not for the input. It's not a B by W by H. It's B by C1 by W by H. That's the input. So for the input image, C1 is equal to 3.
C1 is equal to 3, but by the beginning, from the training set, you only have images. Why you have C1?
So for each image, it has the RGB 3 channel. So that's 3.
Okay. So
yeah.
B, suppose we have this B times 1 upon times 3 times
yes.
W times H. But for the convolution, the first layer, suppose I want my channel to be C1. And I do this C1 times 3 convolution. So what's the output size?
That's one by one.
That's 1 by 1?
No. So I mean, if you only have one small window, so the output is 1 by 1. So, but you will move that small window on the image, so I mean, it will become
all of those windows.
Yeah. So it will become double. So assume the output. I mean, it decided by how you move the window. So there is the stride called the stride. So when the stride is 2, it can be the output can be W divided 2 by W divided 2.
I know. And then I mean, what is the output channel?
Output channel is you can decide it. It's by design. So it can be C. It can be C2. So actually, the real the real dimension of the filter is C2 by C1 by 3 by 3. C1 by 3 by 3. That's for one filter. And if you have if you have, for example, have five filter, that would be 5 by C1 by 3 by 3.
The output channel should be user defined. Like the input channel
isn't the output channel is the number of feature maps? It depends how many.
In PyTorch for the convolution layer, you can define the output, the number of output channels, and the size of the image is defined by is determined by the size of the filter you use.
Yeah, back to Dr. Zhe's question. So if you have a B by C by W by H tensor, and you convolve with a C by W by H kernel, it will just give you a B by 1 by H by H tensor. Then depends how many convolution kernel you used. Then your output, each convolution kernel will give you a B by 1 by H by H tensor. Then you stack them together on the second indices. Then you will have a B by. It's then the new channel is the number of feature maps.
So the C1 times 3 times by 3 and by 3 is the, I mean, the C1 here is the number of filters or the number of output channels.
Yeah, that's something we should be clear, because
Actually,
Channel
in-
cloning, right?
Yeah.
What channel is the output
if you
channel or
do-
whatever?
if you if you implement the convolutional layer in PyTorch, you just need to define the input channel and output channel. You don't need to care about the number of filters. Actually, the number of filters should be the number of input channel times the number of output channels.
Yeah, I'm trying to get some visualization about the convolution layers. So I remember in this class, they provide some very good visualization of the layers, the dynamical figure to do the convolution. Let me.
Hi, Xin.
Yeah.
Here, can you Wikipedia convolutional neural network from the wiki page of the convolutional neural network?
I just send you a link. You can check the. Actually, you can check the documentation of PyTorch.
Yeah.
I just send the link in the chat channel.
What's the meaning of in channel? What's the meaning of out channel?
So for the in channel is the channel of the input, and out channel is the after that one convolution.
Hi, Xin, can you open a Wikipedia? Just open the Wikipedia page of the CNN. Just to
Yeah.
switch. I think they have a good figure of that for that.
Convolution.
And then you scroll down, you can see a structure. They have a figure. No, this is not Wikipedia.
This is not Wikipedia.
This is
not Wikipedia. This is a wiki something.
oh okay. This one, neural network.
I think it's a
Convolution network.
You can just Google convolutional neural network. Yeah, I think this one. Yeah. Let me send it to the channel.
Is this one?
No.
Oh, okay. Yeah. Please send me the link.
Yeah. Problem is that I'm using an iPad. So.
Or you can share on your side.
I think I'm okay.
Oh, okay. I found the visualization of the convolution in this course. So Shibo, for the visualization you are going to send, is that similar to this?
No, it's more.
Okay.
Illustration. Can you open the page?
All right.
Did I send you the page? That page?
Yes.
Mm-hmm.
Yes.
Since his browser was somehow like hijack or something.
Yeah.
I click. It's not the Wikipedia when you when she clicked the link.
You can open the how can I say that?
That's not a link.
Yeah, actually I think I can. So I mean for.
Go ahead, Xin, you can use this figure too.
Yeah, I think let me just try to use this figure to show what is convolution and what's the channel. So so for the input here, actually we there assume this is the input. It has the x there. So for this there is no batch. There is no batch. This is just one single input. So for this one single input, it has 3 channels, x1, x2, x0. So and then we have 2 filters. For each filter, actually, the number of the size of the filter is 3 by 3. The filter size is 3 by 3, and it has for each input channel, it has one 3 by 3 sub filter corresponding to that. So the filter size W1 is 3 by 3 by 3, and they use one bus. So you can see that for the W1, now it became the W1. So for the W1, it will move along the row and on the input image and get one output. So in the green for the output, you can say that there are the small green box. That's the output for one filter. So it means that for the input image, it has 3 channels. The input channel is 3. So the shape for the W1 would be 3 by 3 by 3, and also for the W2, that's 3 by 3 by 3, and there are 2 output channels. So for the output, that's 3 by 3 by 2. The 2 is the output channel. The output channel means that there are 2 filters. Yeah.
I'm still lost. So why there are 2 output channels? It is designated by the user?
Yes. You can decide it. If you want to 5 output channel, you will have W1 to W4.
Well, in convolutional neural network, the learnable parameter is the filters. So the user should define how many filters or local information needs to be captured. So if you want to learn 2 filters, then the output channel is 2. If you want to learn 4 filters, then your output channel will be 4. Depending, it's a user defined.
But here, the filter.
They just
show you have 2 output channels, but why the filter size is still 3 by 3 by 3?
Each channel will correspond to 1 filter. So if you have 2 filters, then we'll have 2 output channel. The size of the filter will be determined by your previous number of filters and your filter size.
So for the filter, actually, it's concatenated by 2 filters. That's the filter that's the W1 and W2. For each filter, the size is 3 by 3 by 3. And actually, because there are 2 filters, so that's a 3 by 3 by 3 by 2. And the input, actually the input is the 3 by 7 by 7 by 3. 3 is the input channel. The output is a 3 by 3 by 2. 2 is the output channel, and the 7 by 7 is the input feature map size, and the 3 by 3 is the output feature map size.
So the input channel, how does the input channel, the channel of the input decides the filter size? So that means one dimension of the filter must be 3?
Yes.
So that means okay, for each channel there will be one slice of the filter to do the convolution.
Yes, if you actually did this, this figure is not really good. So you consider
Dreading side.
Yeah, your input will always be like 3D tensor. So each filter will essentially, the filter is also 3D, right? And the filter will like apply the convolution to this whole volume and get to a value to the feature map for one filter, and it will move like to the right and give you another value of the feature map for one filter.
But have you do you have to make sure that the size of filter should be consistent with the input?
Yes.
You have 3 channels in input, then the filter must have 3 channels as well.
Yes. So Shandian, you can say that for the output. So now in this figure, actually, it's trying to show how the filter, the second filter W1 to get one put. So for the output, it get just the -6, just this single one.
Yeah, but by setting up the yeah, okay, I got a point. So and then by setting up different stride, doesn't mean like you can also maintain the size of the input.
Maintain the size of the output. So here,
like if your input size is 7 by
Yeah.
7, it is possible to have your output size to be 7 by 7 as well, right?
You need to
yes.
pad.
Yes, if you do the padding and also the stride is 1.
Okay.
So for the stride is 1, it means that, so for the for example here, I mean here the stride is 2. For the stride is 1, it means that the I need to draw. Yeah, so the first filter.
And then you just move 2 steps to the left and to the right, right?
Yeah, currently it is. So this is a filter, and then it move to its right. So the center here is the center of the first location, and then this is the center of the second location. So you can say that the center just move to the next.
That's stride 1.
Yes, and if you move like this, it means that you always have the center for each pixel. Then the output size will not change. I mean, but here the if we actually there is only 5 by 5. Okay, this
That
is
doesn't matter. That
after
doesn't matter.
after.
Yeah,
Yeah.
yeah. That's those kind of details are not worth exploring, but I just want to make sure how do you define a filter. So that means the filter. Okay, now I can understand why the PyTorch library requires you to give the input channel and output channel. The input channel must be consistent with the channel of the input. The output channel is designated by the user.
Yes. So you also know what is channel, right? So so this is one channel. And so for the output, it has two channels, and for the input, it has three channels. And for one output channel, it corresponds to one filter. So for the first channel of the output, it corresponds to the W0. For the second channel, it calculated from W2.
Okay, and then you said filter pruning. That means you can preset a large output channel, but then you just truncate them out, or kind of discard the output.
Yeah, yeah. So if you prune one channel, it means that you can totally discuss W1 or W2. So that would be a lot. When we try to prune a filter or weight, it means that we just so for example in W this is I think this is W0000 for this element. For this is one weight. When we prune with the base for the weight based pruning, that we try to prune a single weights. And when we prune the filter, actually we will discard the whole filter. It's equivalent to channel based pruning. Yeah.
But then go back to the batch normalization. Maybe we can go back to the slides.
Yeah, sure.
How they this batch how they put L1 to the batch normalization.
Yeah. So for the batch normalization, yeah.
Maybe I have a question for you. What is the scaling factor? Is the L1O of the
scaling factor
or?
is learned. It's learnable. So for the it means that for so for here this is the one input. This is one input channel. So for could you ask again?
What is the scaling factor?
So the oh, okay. I see your point.
So the factor should be multiplied directly to the whole output channel, right? One output channel is associated with one scaling factor. But you can view like, okay, CG1 is your one output channel. The whole output channel itself is multiplied by some factor S, and CG2 multiplied by another S. Then we want to add L1 regularizer over S. So if S is truncated to 0, then the whole output of CG1 is just throughout.
So it seems
I
to me.
think the scaling factor should be applied to the input channel, and
Yeah.
based on the result and do the convolution operation, then get the output channel. If the scaling factor is very close to 0, and the input channel should be discarded, and you get a compacted network.
Yes, I think from this figure, it means that scaling factor applied to the input channel.
How do you determine how many green layers on the right hand side? So it is also determined by the user.
You mean how many channels to prune in each layer?
No. So after pruning, yes. So you map the original number of filters to a small number of filters, right?
Actually, the green layer should be determined by the scaling factors in the next layer. You can stack this structure together, and
so
the number, yeah.
It's like you say the ice consumption layer. It's actually the input to the next layer, right? It's the output of the last layer. Then
yes,
we are determining whether we want to use all of it as output channel, or we just want to use some of the channel. Like we are turn off some channels of the previous output layer, or it's equivalent to set the output to 0. Is it correct?
Yes.
Okay, then what's the scaling factor?
So the scaling factor will where a learnable or trainable variable multiplied to the output of each channel.
Then if we want to turn it off, it should be 0. Then what does the scaling factor mean?
It's equal to 1.
What?
I mean, if the scaling factor is equal to 1, so it would be equivalent to the original network, right?
You said you want to prune a layer, right?
If we want to prune, we expect the scaling factor is equal to 0.
Yeah, then it's not 0. So what's the meaning of the scaling factor? It's small.
There might be a threshold for you to decide whether that channel should be
yes.
discarded.
So the scaling factor has a meaning, like the norm or the importance or anything, but it has a meaning.
The importance, it indicates the importance of one channel. So if the scaling factor is large, then it means that the channel is important.
Okay, so we are not directly multiply the scaling factor to the input and then do the convolution. It's just a indicator to represent whether we want to prune it or not, right?
We will do both. So it's on one side it's a indicator, or we can say that we can rank the scaling factor to decide the order of the channel to prune. On another side, where in this method, it also multiplies the scaling factor to the input channel. It will do both. So you can say that for the output channel CJ1, actually it's equivalent to I mean the one after. I mean that's the weighted summation.
Yeah, you like it. You have another weight to multiply to each of the channel. then what is the pruning step? If we simply multiply some weights, it's not pruning.
Yes, so it will force for the small scaling factor, like Jen said, there will be a threshold. When the scaling factor is smaller than the threshold, it will be forced to be equal to 0.
Okay, so say we are during the learning or training process, we are adjusting the scaling factors, and then once they go
yes,
they go below some threshold, then we set it to 0.
Yes. So we will learn the scaling factor, and as you say, there is one penalty term in the loss. So that's the G gamma. So for the G gamma, it's equal to the absolute value of gamma. So it means that when the scaling factor is large, the loss will have more penalty on that scaling factor to force it to become smaller.
What's gamma?
Gamma is denote the scaling factor. Actually, that's also the S here. That's gamma. Yeah.
All of the scaling factor.
Yes. For each channel, it has one scaling factor. So how many channels you have in the network, it would be one vector.
I see. So it's just the L1 norm applied to the scaling factor.
Yes, or L1 norm. Yes.
You use L1 norm to select the output channel.
That's a regularization on the scaling factor. So that's the penalty. It will force the scaling factor to be close to 0. And this is trainable in the network. So for this method, actually, so in this paper, that's the learning efficient convolution network through network slimming. That in this paper, I mean, it tries to do the pruning during the training. So the I will show the flow chart of the network's network pruning. Firstly it will train with the regularization on the sparsity on gamma, and then it will learn the scaling factor. So it will sort the scaling factor, or actually here it doesn't need to sort, it just use a threshold. And when the learn the scaling factor is very, very close to 0, it will force it to be 0. It means that it will prune that channel. After pruning, it will fine-tune this network. So in the whole training, it will repeat this procedure until to get the final well-trained network.
Okay. But yeah, let's go to the batch normalization part. I'm just curious, how do they do the batch normalization? Unless they all the outputs in one channel share the same, share the same variance or whatever. Otherwise, how do you? Okay, X in minus mu of B, right?
Yeah.
Yeah. So
I can help explain this part.
Okay.
Actually, for the batch normalization, it is a channel-wise operation. First, you just do the normalization for this batch using the mean mu B and the standard deviation sigma B. And usually in the PyTorch implementation, there are two more learnable parameters called a scaling parameter and the shifting parameter, gamma and beta. So they just directly use the gamma here as the scaling factor in their method.
So gamma and the beta is shared by, I mean, each channel, all the outputs in one channel.
Yeah.
Share with one pair of the beta and gamma, right?
Yeah. For different batches, the gamma and beta are the same for each channel.
Okay.
So this is only an implementation trick, I think.
Yeah, this is like group plus O.
Sorry.
I mean, this is like group plus O. You put L1.
Oh, okay. Yeah.
You can see you put L1 on all the outputs of that channel, but here you just multiply a scaling factor gamma here, and over for all the ports in one channel, you multiply them together with gamma and plus beta.
Yes. So actually,
the one issue is that if your gamma goes to 0, you should make sure your beta goes to 0 as well.
Yeah, that's a good observation. So it do some so actually it also extend the scaling factor on the shift term.
Okay.
Yeah.
Okay.
So this is the modification on the batch normalization.
Okay.
So is there any other question about the batch normalization or the channel-based pruning? Okay, then I will continue. All right. Okay, so actually this is this paper have very high citation, so it's a very popular method to do the channel pruning, but it still have some drawback. So for the problem for this one is the stability. Actually this method is not stable. So it means that as we discussed just now. So for example in the first batch we can get a scaling factor like point for example here 1.170. Then in the next batch maybe this scaling factor would become close to 0. It's possible. It means that in some subsequential batches, actually the scaling factor vary a lot. But we know that if the scaling factor is too small, we will discuss that. So it means that in different batch, one pruning sometimes is kept, sometimes it's pruned. So it will make it very unstable, and this unstable can impact the network performance. Actually, I try to say whether I can. I try to check whether there are some figure in this paper have the figure like on the right. I didn't found the change of the pruning ratio during the training. So for this figure come from my previous paper. That's the learning strict identity mapping in the deep residue network. In that network, it's also a method to do the pruning during the training. Actually, I encountered the similar problem that the pruning is not so stable.
So in practice, when I do this, it's just run like a few epochs, and then prune the channel with the threshold, right? and fine tune it and then redo this.
Yes.
And how
So-
do they implement the L1 regularizer? Or they just use the default library to provide some operator to do the L1 regularizer?
Here.
Yes.
So you just so actually we define the loss function by ourselves, right? So the first term, the L1, we just we need to know we need to get the variable gamma in each layer, and then just apply the L1 norm, do the summation and add it to the loss.
So the L1 norm is provided by the PyTorch library or TensorFlow library, right?
No,
It's just the type of the
we can customize that.
I mean, when your objective function, their implementation is just summation of the absolute value.
Yes. Yes.
That's very stupid.
So what do you expect?
Because it's knowing that if you do the stochastic optimization by straightforward putting some absolute value and use, if you're doing that, you're actually doing sub-gradient descent. That won't give you sparsity. Anyone who knows sparse optimization, sparse learning knows that problem.
Sorry,
I thought at least the PyTorch or TensorFlow should provide some operator on that. Like you either do some proximate operator, or especially in the stochastic learning procedure, there's knowing some method like FTRL. You can do stochastic training while you can still maintain guarantee some sparsity results of the coefficients. If you simply do the sub-gradient descent over this absolute value, it won't give you sparsity.
Okay, yeah. So yes, for this L1, it will not give you make any gamma equal to 0. We need to do some additional.
Rank or using some threshold, right?
Yes, and then you need to reset the gamma I equal to 0. So that's why we need the fine tune in this algorithm.
Yeah, that's why I feel really weird, because if you really do the optimization, if you have an effective stochastic learning algorithm, you should be able to converge, right? And after converge, you just prune out those channels and do fine tune again. That should be enough. There's no need for this iterative procedure.
Yes, if the PyTorch provide that function, yeah, it will become easier.
Okay. Yeah, let's go ahead.
Okay, all right. Okay, so that's the problem of this method. It's unstable. Not the prediction. So the scaling factor will not be stable, and it will lead to the shape of the compact network to be unstable. So that's why we introduce the Bayesian method here. So instead of one scaling factor for one deterministic scaling factor for each channel, we introduce a distribution for every scaling factor. So you can say that here that's the norm that's the Gaussian distribution on each each scaling factor. when their mean is close to 1, they will keep that channel, and when the mean is close to 0, it will discard that channel. So with the reason is that I think when we use a distribution to describe one scaling factor, it's possible to get the global information. I mean, from all the batch, it will collect the information from all the batch instead of from one batch, from the local information. That's my understanding why this method can somehow do better than the previous method.
But what's the prior over eta or gamma?
Yeah, I will cover it later. It have different choice. So we have 2 paper. So actually in this paper, in the variational convolution neural network pruning, it used the Gaussian as the prior, and use another paper Dirac that's used the Dirac distribution.
So you mean both papers are actually learning and pruning, right?
Yes, for this one, this is
Output
learning
pruning.
and pruning during learning. Yeah, it's learn to prune.
Okay, but what's the difference between this paper and
The
Da has presented?
distribution are different. One is use the normal, one is use the Dirac. There is no much difference, and yeah. And another,
Okay,
yeah.
for the variational convolution neural network, how do they estimate the posterior of gamma? They use variational inference framework?
Yeah, I will cover it one by one.
Okay.
Okay, so here it introduced the variational inference on the channel importance. Actually, that's the scaling factor. So let's look at the problem. Let's consider D as a data set. So there are data and sample, and X is the input data, and Y is the label. And so for this problem, the gamma still denote still mean the channel importance or the scaling factor. So our goal is to learn the conditional probability P given X and gamma. So for the original learning target is P Y given X. So now there is one there is we also need to consider to learn the gamma and get the Y. Actually, there should be W, the model itself, W P Y given X W. It ignored that in the notation in this paper.
W are the filter weights, right?
Yes. Okay. And then if we want to learn the gamma, then we need to learn the posterior distribution of gamma, the P gamma given D, and we know that we can get this with the Bayes rule that's equal to P gamma multiplied P D given gamma divided P D. So for this one, as we know, PD is not a computational intractable. Because in this integral, because for the integral we need to consider all the possible gamma.
This one everybody knows. Just go to the next step.
Yeah. How do you evaluate the likelihood, like the P Y given X and gamma? How do you evaluate that? Gamma is the scaling factor, right?
Yes. How do you evaluate that? Sorry.
How do you compute its value given given the gamma?
PD given gamma, right?
Yeah, right.
Yeah. So actually if gamma if gamma is known,
It's just like the
PD.
Gaussian error,
The
right?
Gaussian likelihood or cross entropy or Bernoulli likelihood or categorical likelihood. It depends.
If it's binary, it should be like some cross entropy. If it's classification, if regression, it should be Gaussian likelihood or
I
something
think
like that.
gamma just relates to some kind of structure of the network, and based on each structure, you can get some output and then calculate the likelihood based on the output.
So it's still some softmax distribution like the cross entropy. Yeah. The gamma is
I see, but actually, I'm also curious here. Do you mean that for the PD given gamma is equivalent to the likelihood?
I got confused. I got confused. I think because gamma is given, then you forward past the neural network, you should get some predictions, and you can it's the same thing like it's the same thing calculated. It's the same, still the same likelihood. Sorry, I got confused. I think gamma is something else.
Yeah, but yes and no. So I think I'm not actually I'm not sure the PD given gamma is the likelihood. I think it's still a little different from PY given X and gamma. So when we use the variational inference, actually we didn't need to calculate the ride of this equation. We just use another way to estimate the P gamma given D, right?
Yes.
Yeah. So actually, I think for Shibo's question, how to calculate the PD given gamma, is that really equivalent to be the likelihood? I don't know.
I think it's the same thing. It's still the percentage.
Yeah, move to the slides. Move to the next slides. We should be able to see that.
Okay, so in the next slide, I try because actually I didn't understand the variational inference before this paper. So I try to look at some document to say how to understand it. So for the variational inference is that we so there assume there is one system. So there X is the observation, and the theta is trying to model this system, and Z is some hidden variable. So for example, we toss the coin, and it follows the.
You don't need to give tutorial of variational inference. Everybody knows that. It's very familiar.
Except me.
I mean, if you still
Okay.
have, I mean, something unclear, we can schedule time, 10 minutes.
Okay, all right. So okay, if everyone is now that's great. So actually for the variational inference, it is that we would like to learn the posterior PZ given XZ. It's the hidden variable, and but it's intractable. So we try to estimate Q theta for Q theta for that, and then we need to minimize the difference of those two distribution by KL divergency. When we and for KL divergency, actually we can say how to calculate it. Actually, it's equivalent to the evidence subtract the eyeball. So from this because the evidence px given theta is the model. So for this, actually, it's not related to the z. So we can just consider it as a constant. So we can say that the KL divergence is minimize the KL divergence is equivalent to maximize the abel. That's a conclusion. So then let's go back to the channel pruning, and so we need to learn the posterior p gamma given D. So we want to use a parametric matrix, the distribution Q phi.
Oh, okay.
Q phi gamma.
I just want to confirm one point. So
yeah,
they do this. Meanwhile, they estimate the filter parameters, right?
Yes. This is during training.
Yeah, we can go to the next slide.
Okay.
There's nothing new here. It's just
okay.
So maybe I have missed some slides because there was a call. So after they estimate the distribution, and what do they do to do the training? So if they have the posterior of gamma, then what do they do to the distribution?
Yeah. We were. There is still some detail we needed to. So for the elbow, we needed to say how to calculate this, because
you can skip this class. We're doing this every day. Yeah, this is really tedious. Yeah.
Like we have covered it or not? Like how to, once we got the distribution, then how do we do the pruning?
Yeah, once we got distribution of Q lambda, like we can rank the posterior distribution of lambda according to their mean and variance, right? How they do that? They just prune the network, or they also do some iterative procedure?
Oh, we haven't got to this point. Oh, okay.
Yeah. Actually, it still do the yes and not. So it still do the okay. So maybe let's look at the algorithm firstly. So in this procedure, it's still pruning during the training, but it don't have the fine tune.
Oh, I see.
That okay. I think that's because it use the Bayesian distribution for gamma, and it's more smooth than the previous method. That's the advantage of the variational inference. But that's still yeah.
Yeah, the reason is that if you use L1 is known as a uniform shrinkage. So that means no matter your weights are useful or not, you're gonna try to shrink this, and this is not favorable, because for some weights which are useful, you don't want shrink. It's a skill. You still want to estimate from data. I mean, totally data driven.
Yes.
But if you use L1, it breaks that property, so they have to fine tune that.
Yes.
For the compensation. But here, if you just use Gaussian distribution, it doesn't have such deficiency, so they don't need some fine tune. That's my thought.
But after training, I have a question about the algorithm.
Okay.
So from line 7 to line 11, so after the pruning, they basically remove some filter channels, right?
After each iteration.
Yeah.
Sorry, each iPad.
Then the scaling factor, or the gamma size, also changed.
Yes. So the gamma is also in the batch normalization. So it's part of the learnable parameter here, right? And actually, there is one thing I'm also a little confused. So that's line 6 So for the line 6, that's the up parameter. I'm not sure I mean, we know that for each epoch we have many iteration, many mini batch. I think to update the weight itself, we need to update the weight after each mini batch, and but here it's just mention update the parameter in each epoch. So I'm not sure whether they just update the does that mean they only update the parameter, no, update the scaling factor at the end of each epoch? I didn't find their code, so that's the thing I didn't figure out.
Yeah, that's a good catch. But if they just fix W, like in line 4, in line 5, just fix W and update 5, that would be extremely expensive, right? Because whenever you update the parameters, the W1s, you have to optimize the elbow to update Q5.
Yeah.
That's pretty fun.
Yeah. So actually, I guess they update 5 and W together.
Yeah, then you can do this. But then there's a problem if you just update them together. Then do they mean that after every update they're gonna check if each scaling factor, the UI and the sigma I is less than some tolerance, or at the end of that epoch?
Oh, okay. So I guess that at the end of the epoch, they try to do the
yeah, that makes a lot of sense. Yeah.
Okay.
Yeah, the for loop is for the whole epoch. So
yes,
they will train for a whole epoch, and at the end of the epoch, they will decide which channel to prune, and then go to the next epoch. And
yes, I guess so.
And maybe the W will also change, because if we eliminate some channels, then the number of parameters of the neural network itself will also change.
Yes, prune one channel is equivalent to discard one filter. So that's how to get a smaller network.
Okay.
All right. And so yeah, I know you are all of you are very familiar with how to calculate the eyeball, but I think there is still something I need to mention. So because they have some spatial formulation for them. So in this eyeball, there are two terms. The first term actually that's the log py given x and gamma. Actually that's the prediction probability. And for this, we know it's equivalent to minimize the prediction error. So and the problem there is the expectation over the Q5. So for this one, actually they use the parameterization trick. In this paper, they didn't provide the detail about this trick. So I just go back to the paper auto encoding variational bias to get the detail. So what they do is that actually instead of get the expectation, they use some sampling. They have some sampling over the phi, and the epsilon here is somehow like some noise. It's epsilon follow the distribution of the normal distribution. So every time it do the sampling on epsilon and then decide the phi.
Yeah. This is standard technique.
Oh, okay, it's a standard. I didn't know it before. Actually, I spent a lot of time to understand this part. Okay.
Okay. Yeah, you waste your time. You should ask. I mean, you should discuss with Jun or discuss with Shibo. This is something like I wouldn't say like all Bayesian inference right now. They are all using reparameters in trip.
Oh, okay, okay, all right, and okay, that's great, and
I just want to have a quick check. So now when we do reparameter check, do we only sample one sample, or do you use multiple samples at a time? Normally, I
guess
use only one.
I think Shandian may know the answer.
Just one.
Just one.
In most of the cases, just use one sample.
You use one, then sometimes the it will convert extremely slow. Did you notice that?
Yes.
Why it's slow? I didn't get that.
Because of the variance. The variance of the gradient will be too big, and you are not going down to the correct direction. But that's another topic. Okay.
So you mentioned the implementation, or
That's an implementation. This is not I mean, this is tunable. It's not the key part. I want to know the idea.
Yeah.
Like if you feel it converges fast, converges slow, you can just sample multiple epsilon and take the average. And I mean, take average of the reparameterized log likelihood and do that. It doesn't matter actually.
Yeah,
I mean,
it doesn't. Yeah.
Let's look at the dirichlet part.
Okay. So and okay, there are some other another assumption.
Nothing surprising here. So just come back. This is too easy. Right? It's too straightforward. Yeah, we don't need to waste time to look at this.
Okay. So, yeah. So ever we are going to give out some experiments result here. So for this one, just compare with the baseline. For the baseline, that's the original network without a compression. And as we know, so it's decided by the pruning ratio will be decided by the threshold. If you we can check this. We can check this figure. So if the threshold is large, it means that it will get a smaller compression rate, but higher accuracy. And if the epsilon is large, then the compression ratio can be larger. But meanwhile, it will damage the accuracy. Is that it makes sense, right? So in this paper, in most experiment, it use some thresholds, not too large and not too small. That use the there is a tau is equal to 0.02, and that's the hyperparameter used in all the experiments. So with that one, for each network, it will have different pruning ratio. And for this paper, when talking about the pruning ratio, it tries to say how many channel is pruned, and how many parameters are pruned, because the size of each channel, or we can say the size of each filter can be different. So the two pruning ratio for channel and for parameter are different. And additionally, it tries to calculate the FO flope. The flope actually it's a metric for the computation, because the computation for the FC layer and for the convolution are different. So it use the three metrics to estimate to evaluate the compression.
So the flops are evaluated after the pruning or
After.
okay.
Yeah.
So in terms of computational complexity or computation resources, it didn't provide like a reasonably good result here.
What you say not reasonably good result? You mean the accuracy, or you mean the compression ratio is not high
The
enough?
compression ratio is not high. So when we say pruning, maybe we tend to like have some 1 to 9 or 1 to 10 ratio.
Yeah. So the shortage for this problem is that we cannot ask this method to arrive the target sparsity. Assume we need to prune 90% of the network. This method cannot do it because it can adjust the hyperparameter of the threshold. If the threshold is larger, it will have higher compression ratio, but always it can not achieve the target sparsity. Yeah, so and also it tests on the other data set, C500 and the ImageNet with the other network structure. So I would like to say because I in my own paper learning the strict residue network, I also test on ResNet. Actually what I tested is ResNet 152, not 164. Yeah, there is no much difference. So but I would like to say the pruning ratio is somehow a little better than my method. So I would like to say the pruning ratio is not that bad, because the accuracy, it almost didn't change the accuracy. Just a drop
164 means 164 layers.
Yes, that's a very large network.
And also they just prune the channels. So ResNet does not only include the convolutional channels, they also include the feed-forward layers, right? Or you call linear layers. And still
they only prune the convolution layers in this method.
So I mean at their pruning ratio, which is to 27.16%, their accuracy is pretty good.
Oh, sorry. Which one do which?
You mentioned ResNet 164. So I mean, at that pruning ratio, their accuracy is pretty good.
Yes.
Okay.
Yes, but you can say that for the parameter for the pruning ratio on the parameter, actually that's low.
Oh. But what's our performance with the parameter pruning ratio similarly?
You mean in the combinational pruning method?
70.
I didn't test on ResNet 164. I test use another network.
Yeah, I know that. But
MobileNet.
In a sense, if you preserve 85 or 80% parameters, so is the accuracy almost the same as? I'm just curious to know.
I mean, I didn't test on this network, the ResNet 164, so I cannot answer that. So what I compared is with my previous CVPR paper. I test on the ResNet 152 network, and it's I think the performance the performance are similar, and the channel pruned are better than what I did, a little better.
I mean, the accuracy is basically the same, and the pruning ratio you did is a little bit better here than here.
This method pruning ratio is a little higher.
Oh, there's it's a little bit higher, and your accuracy is basically the same.
Yes, my accuracy is close to the baseline, and this is a little lower than the baseline.
And your method is also like training plus pruning.
Yes.
Okay.
Yeah. Yeah, and the last is the performance on the ImageNet.
And the ResNet 50, did you test the ResNet 50? I forgot. It's ResNet 20 or ResNet 50?
For ResNet 50, I didn't test it. I mean, I tried to test it, but for the CBS, I found the greedy algorithm doesn't work well on ResNet 50, so I didn't continue on that architecture. Okay. Actually, for this method, it also have some comparison with the other method. I guess the performance may be not that good, because as we know, the paper 2027 is the previous method where the network slimming paper. So in that, it do the pruning and fine tune in the whole training procedure, and for this paper, because there is no fine tune, so it compare with the previous method without fine tune. If without fine tune, this method is better. It's much better.
That's interesting, right? Intuitively, fine tune should make you better.
There is no fine tune. There is no fine tune for both methods.
Oh, really?
Yeah. So
what if they add fine tune?
They didn't show the result. I'm also very curious about that. So actually, I think they have in this one they show the stability. As we can say that during the training, the accuracy I mean, have the trend increase. It somehow can decrease a bit, but not that much. And the compression ratio keep decreasing. Oh, okay. That's what I didn't expect.
What you didn't expect? What?
So it means that for the you can say that so the x-axis is the epoch. It means that the whole training process, and the compression ratio is decreasing, instead of increasing. Because in my paper, so when the network train more, the compression ratio will be higher. For this one, that is the opposite.
But the thing that's it's natural, right? Every epoch you're gonna drop or prune a bunch of channels, and next epoch you prune another bunch of channels. The compression should keep decreasing.
The compression ratio, they mean the number of parameter
to
the percentage of parameter to the original one, right? It should be decreasing. Why not decreasing? Because every epoch it will delete some channels. It must be decreasing, right?
Yeah, it starts from 1.
Compression ratio is start from 0, right? Compression ratio, how to
It's a
how to
pruning ratio. What are you talking about is pruning ratio.
pruning? So compression ratio is equal to pruning ratio.
It starts from 100%, so it's simply the number of the percentage of the numbers that have like left.
So it means that the gamma are 0 as the beginning.
No, the red line starts from 100. So we will keep 100% of the original parameters, and as the
No.
pruning process,
We need to figure out what's the definition of the compression ratio. I think the compression ratio is the remand channel divided. Yeah, let's just check the paper.
but if start from 100, so it's decreasing.
Yeah, it's the
Yes.
number of remaining parameters divided by is the ratio of the remaining parameters in the network, remaining channels in the network.
Yeah, whatever is defined in terms
okay.
of parameters or the flows or the
Remaining.
channels, but it will be decreasing.
Oh, okay. It's a remaining. Okay, it's not the sparsity. Yeah. Then
What you said is a pruning ratio.
Okay. Then it makes sense. All right. So compression. Oh, okay. It's the reserve. Oh, okay. Yeah. Then it makes sense. I'm thinking about the sparsity. Yes. Yeah. So at the beginning, all the channel are preserved, reserved, and finally the sparsity will become larger. Yeah. Okay. There is no problem. Yeah. So we can go to the directly pruning. So for the directly pruning, there is no much difference. So the apple is also as the objective function, and the difference is that the prior and the postural for the parametric on the importance score. So here the SL is the gamma in the previous paper.
But why do they assign directly prior?
That's what I didn't understand well. So
and also the dimension. What's the dimension of directly prior? Because directly prior will gives you distribution over k categories. Like you have k categories, like 3 categories. It will give you a distribution over 3 points, like 0.1, 0.9, 0.1, 0.1.
Yeah. So what I understand is how many channels there are, how many dimension is the
okay
directly.
Okay.
Or yeah, maybe it's in one layer because the SL. We can.
For example, layer L has like 100 channels.
Yes.
The directly prior will be 100 dimensional.
That's what I understand. Let me check. Let me check the. Yes, this is. Yes. So yeah, it requires the scaling vector to be the summation to be 1 in 1 layer.
Okay.
Yeah. So yeah. Then I think for the rest they are the same.
To estimate the posterior, and do they also have like a similar iterative updating and pruning?
No. So that's the difference. So here the one. So firstly, the one difference is that they didn't use the batch normalization they didn't reuse the scaling the scalar in the batch normalization as the scaling factor. This is additional parameter here, SL. But they are similar to because for this method they try to also apply SL in the fully connected layer, because batch normalization are only used in the convolution layers.
I didn't get a point.
Yeah, so for the batch normalization, actually that's one spatial layer can be used after one convolution layer. But as we know, in one network, we always have in the last two layer, it always to be the fully connected layer, to be the linear layer. So for the linear layer, we cannot apply the batch normalization. And the ProWest method has the implementation with the batch normalization. So it means that in the ProWest method, the last two linear layer cannot be pruned.
But if they're just the linear layers, why do they want to? You just want to prune the channels, right?
Yes, but you know, we should know that. So for the linear layer, the parameter set are pretty large. So for example, for the ResNet, the output of the ResNet, it will apply the linear layer. It will so firstly flatten the output of the last convolution layer. It will become D by 1, and the D is already very large. So for example, like the 4096, and then there are another two convolution, another linear layer that would be the output would be 1000 and 1000. So it means that the parameter set would be 4096 by 1000. That would be large, but with the
ProWest wants to prune the
linear layer
as well.
Yes. So it introduces the additional scaling factor instead of reuse the scalar in batch normalization.
But I think the topic is like channel pruning, is not the general pruning. So
yeah. That's my problem. I try to put them together.
But for the previous method, if you apply the batch norm to the for the connected layer, you can also prune exactly the same way. I didn't see there's a problem that they can prune the for the connected layer is the advantage of this method. You can also prune the FC layer using the previous method.
No, we cannot, because the batch normalization is not applied on the linear layer.
I mean, if you applied it, then you can prune it the same way, right?
Yes, but we didn't. No one do that. I didn't know why batch normalization is not used in the is not used in the linear layer. I think there should be some reason.
Also, I mean, in practice, most cases, batch normalization is only applied to convolution.
Yes.
Really?
Yes, I believe so. I never say architecture use the batch normalization after the linear layer. You can check it.
Okay, but why not? What prevent them from applying those pruning technique to the FC layer? Have they tried, or they just don't want to use?
I believe people have tried that. that's a very simple strategy. I believe people have tried that, but the performance is bad. Why is bad? I think batch normalization can provide somehow the regularization to the network, which will avoid the parameter exploration, not exploration. I mean, is to avoid the parameter to become too large.
Actually, the VN is initially invented for the FC first, then they generalize it to the CNN, not the other way around.
Sorry, could you say that again?
Batch normalization is first invented for the connected layer, then people generalize it to the convolutional neural network. So
I didn't know that. I mean, but in practice, I can check it offline to say why the batch normalization are not used in linear layer now.
Okay, that's yeah. You guys can talk. Yeah,
I think it's
I
interesting.
I also learned batch normalization from feed-forward network. But anyway, so how do they apply their Dirichlet? So here you mean they apply the Dirichlet prior on both the channels and the feed-forward, the linear layers?
Yes. So and there is another difference. For this method they use the retrain.
So they multiply SL with ZL or HL?
ZL.
So ZL is obtained by sigmoid, I mean, some transformation of HL element-wise product with SL?
Yeah, the final output is ZL multiply SL.
ZL multiply SL?
Yes, ZL is equivalent to ReLU of HL.
But they also multiply SL. What does, I mean, SL is applied before the nonlinear activation or after nonlinear activation?
After
nonlinear activation.
Yes.
Okay, and this is for every linear layer.
Yes. And another difference is that this is only used for post training. So it means that it applied on a well-trained model, not pruning during training.
Oh, that's something interesting. That's something related to our goal, right?
Yes. I'm not sure. Whether it's the Dirichlet make this possible, makes the post training pruning possible.
For the previous method, they could also use the same procedures. Right? You can fix the neural network parameter, but only fine tune but only train the gamma, and then
yes,
after.
I guess so. But I didn't found some follow-up work to do that. I mean, maybe
like they decide to do this like differently because of what, or there's a convention to do it this way, or each paper decide to do it in their own way and see which one is better.
Yeah, they have a comparison. So in this one, the VP is means that the variational convolution network pruning, and the Dirichlet is the current. It has already become the state of art, and it have so the error. Actually, the error is not too. The error is not small enough. The error is larger, but the network it can prune much more parameter.
What's the error?
Error, it's the
This test error.
prediction error in percentage.
Okay, so it's much worse than VP.
Yes, but you can compare with H rank or BC GNJ. I didn't check what's the BC GNJ, but H rank is also very popular method to do the channel-based pruning. So for this one, and the parameter, the remaining parameter is half, and the performance are better. So I think this method is not bad. And for VP, the parameter is about 5 times than the direct late.
In this kind of work or in this area, what was the evaluation like? Which one is better? Someone achieved a much lower error, but
yeah, error is lower is better.
Yeah, then for now from this table for digital MVP, what do people say about the two methods? Like you need to choose depends on your use case. If you want a higher precision, then you use VP. If you want a smaller network, then you use digital.
Yeah, yes, I think so.
Okay.
Yeah, I
Yeah,
guess
so
we have to anything to summarize.
yeah, so it's almost done, and there is one additional thing about the visualization. So because it's also talk about the benefit of the basic method used in the channel-based pruning or the neural based pruning. So the benefit is that it makes the pruned channel, which the choice of the pruned filter to be explainable. Yeah, that's it.
Okay. I think Xin, I think next Monday you're gonna present the remaining few papers you just mentioned.
Okay, that will be a lot.
Yeah, we can discuss a little bit more about this Dirichlet pruning. At least we need to know what's the motivation of using this Dirichlet distribution.
Okay, I will check the direct paper again. I feel it didn't discuss the different compare the direct with the Gaussian distribution much. Maybe I didn't pay attention to that. I will check it again.
Yeah, because you know, last year when you started that combinatorial pruning task,
yeah,
I was thinking if we can build a Bayesian model to do that.
Mm-hmm.
It looks like somebody has done that, but it's not. I mean, it's not formulating in our as in our framework. But at least it shows that leveraging some Bayesian inference can still get pretty good results. But I'm not sure like what's the strong reason of applying Dirichlet distribution, right? So
okay, so
people have developed like a concrete distribution, right, to parameterize those and to get a continuous relaxation of those categorical variables. And why do they go back to the Dirichlet distribution? But finally, I see that they have found a way to reparameterize the Dirichlet distribution.
Yeah, and Shandian, I would like to say, actually, the objective function in this Dirichlet paper is different from what we tried last semester. In last semester, we try to optimize the delta W multiply Hinch matrix multiply delta
I mean,
W.
it's not the same framework.
Yes.
Actually, the probabilistic framework I like it better because you essentially do not assume approximation at the beginning,
Mm-hmm.
right? But But the problem is here, why can they assign prior like this? And also, if you want to assign derivative prior, it should be uninformative at beginning. I don't know how to set hyperparameters. Like what is the derivative prior? What is parameters of the derivative prior? Are just all ones or?
Yeah. So for the, do you mean for the alpha zero?
Zero, yeah.
For the prior, they are one. They are the same. They assume all the parameters have the same prior.
One is a little bit strong. If you want to be less informative, you should make alpha 0 to be quite small. It should be very large.
Yeah.
Okay, but then, yeah, they explain that if we put alpha 0 to be less than 1, they put probability mass toward a few components bigger than 1, all components become similar to each other.
Yeah, they have explained that in the paper, but I think alpha 0 or 1, and in the posterior they discuss the phi L. For phi L, if they greater than 1, and if they are smaller than 1, they discuss that.
Okay.
Okay.
I mean, I'll ask that. Like, you can see that if we just switch derivative prior by the Hausdorff prior, we can do the same thing.
Okay.
Right? Onda?
Yes.
Yeah, you have done a lot of things like network pruning. It's another like tensor network pruning things last semester, right? But here we can just shove the Hausdorff prior in. We place the Hausdorff prior over the scaling factor. You can still prune that.
Mm-hmm.
Yeah, I mean, there seems a lot of choices.
Yes. I mean, for the computation, to make because another thing we need to pay attention. We need to make the able to be differentiable. So if we apply some Hausdorff prior, is that possible to make it differentiable?
Yeah, you can do variational
Okay.
inference. You can do reparameterization tree. You have all kinds of things you can do.
Okay, cool.
Yeah. We should discuss about this direction. Previously,
Okay.
I thought this kind of methods are really trivial, but you can see that they can still publish in stats, CVPR.
But I think the contribution for the direct later pruning is not that much. I mean,
that's my question. Yeah, that's my question. If you just replace a Gaussian prior by a derivative prior, what's the strong motivation? What's the benefit?
Okay, I need to read the paper again because I read the direct later pruning first, and I found the formula they didn't provide much detail about the formulation. So I go to the variational convolution pruning and put more time on that.
Okay, that's good. That's good. Yeah, let's continue the discussion on this next Monday. Yeah,
so I would like to say I think even I used 2 seminar in next Monday, so it's impossible to cover all the paper mentioned here. So my prior will follow this. Firstly, yeah, follow the I'm more interested in the distillation and the quantization. Okay, all right.
Okay, great. Thanks, Xin.
Okay.
Yeah, let's
okay, thank you.
Yeah, everyone has a good weekend.
Thank you.
Yep,
Okay.
thanks.
Okay, bye.